Figure 1 shows the magnetic field produced by a current in a long straight wire. So you can see a current going this direction and the magnetic field is running anti-clockwise. Which row of the table is correct when the strength of the magnetic field is greatest? So the magnetic field around a wire is strongest nearer the wire, and obviously if you have a larger current running through the wire, you're going to have a stronger magnetic field. So this is the only one which fits that criteria. Which of these materials would be most suitable for making a temporary magnet? Iron. You see, with iron you have basically particles in the iron which can move. So let's say this is an iron bar, particles which maybe we call domains, which may be facing in different directions, but you can magnetize these, and when you do, they all line up in one direction and it becomes a magnet. You can either do this by using an electric current, because the magnetic field generated from an electric current like this one, we'll call them all to line up, or you can basically get another magnet like a normal bar magnet, and you can basically move it in one direction, circular like this, across, so the field lines intersect with this and cause these all to line up, so they sweep these domains in the right direction. Figure 2 shows a magnet holding some paper clips. Describe how a student could show that the paper clips are induced magnets. What that means is describe how you could show that these paper clips are temporary. Their magnetism is due to something else interacting with them. Something else has created that magnetic effect within these paper clips. So it's quite simple. All you have to do is remove the magnet and the paper clips will no longer attract each other. Describe how you could show that the Earth has a magnetic field. You would basically, for example, you could just use a compass, or basically you want a magnet which is able to turn freely. And what will happen is, for example, you could either place a magnetized pin on water, or you can hold it to a piece of thread, and it should turn to align with the Earth's magnetic north pole. So use a compass, the needle always points north. A student uses a compass to investigate the magnetic field near a bar magnet. The student places compasses near the bar magnet as shown in figure 3. Make the north pole of the bar magnet with an N. So what's important here is to recognize that field lines always travel from north to south. So we can see this is pointing this direction, so it would go like this. So that being the case, and there'd be another one here, for example, and that being the case, we know that this is now the north pole and this would be the south pole. State 2 ways in which the investigation could be developed to show the shape of the magnetic field around the bar magnet. You may add to figure 3 to help you with your answer. So one simple way is you could actually add more compasses and you'd end up seeing the pattern. Or you could use something, just because compasses are quite big and limited in how many you can place down because they take up a lot of space. But if you use something like iron filings, they take up very little space and they act like mini compasses aligning themselves with a magnetic field, and you'd see a pattern. So quite simply, add more compasses or add iron filing.